And we're live.
Hey everyone, welcome to the 5th episode of the Stanford MLSys seminar series. We're back in with another episode. Let me introduce the cast again. I'm Kran. We have with us Dan, Fyodor, Matej, Piero, and of course our speaker today, Chip Huyen, who will be discussing with us principles of good machine learning systems design. So as always, the plan today is going to be a 30-minute talk by Chip and then a 30-minute podcast style discussion where you, the audience, can ask questions. So you can post your questions in the live chat and keep them coming. We'll keep watching for questions and we'll kind of compile them for Chip for the 30-minute discussion at the end. So let me introduce our speaker today very quickly before we dive in. Chip is an engineer who develops tools and best practices for machine learning production. She works at Snorkel AI right now, and she's got a lot of industry experience, obviously, with Netflix, NVIDIA, Primer. A lot of people probably follow her on Twitter as well. She'll be teaching machine learning systems design at Stanford in January. And she's also the author of 4 best-selling Vietnamese books on top of everything else. And today she's going to talk about principles of good machine learning systems design and tell us a little bit about her thoughts around that. So Chip, take it away. And thanks for joining us today.
Hey guys, it's Chip. Thank you so much for having me. So I was like extremely excited for today because I really like I guess I realized Stanford is my favorite school. Totally unbiased. I don't know why. And I really enjoy. I'm like a big fan of what everyone is doing as a lab. I'm like Matej, like he's here and I'm just like very nervous just like seeing him here. So thank you guys. And so today I'm gonna talk about some things that I have been working on. So it's a new talk. So usually there are like some slides that is like work in progress, and I like the live streaming format, so we can get like take like in like online questions and discussions. So if you guys have any questions in the meantime, feel free um, to ask. And I would really love to hear your feedback as well. So today is a talk on principles of machine learning system design. And so for introductions, my background, I think you guys have made a very kind introductions. So my background is in writing. So before, when I came to Stanford, actually I wanted to do English literature. And I remember at that time, my one of my friends was like, "You're never gonna make any money off it." So at that time, like Stanford was like as a peak of the AI hype. Please don't hate me for calling it a hype. So I took like I joined some CS courses and some AI courses. And I wow, this is super fun. So I switched to AI. And I did some like product and some AI stuff. So currently I am with Snorkel, which is an end-to-end platform for building AI applications. So my boss, our CEO, Alex, was just at the same seminar last week. And I think he talked a lot more about this. So you guys are interested, like by his talk. Alex is a much better speaker than I am. So for today, I'm gonna talk a little bit about talk about machining, not a little bit, like the entire talk about machining productions. So the first is about the machining in research and production. I went pretty skim this quickly because I think you guys are like in MLSys, you guys are like experts in this. So the second is like some of the machining production myths that I have encountered. The next is I would like to introduce this like there's some things that I think like a process that makes sense. I think I noticed that in the industry, machine learning is still fairly new and everyone is still doing like their own thing. So I'm just hoping that like maybe it's a discussion for some standardization around the process. And then next is the 4 phases of machine learning productions and with some principles that I think would be like interesting to keep in mind when we build a system. So for the first topic is machine learning in research versus machine learning productions. So there are several things, and I'm just gonna go through the 2 main things. Is first the objectives, and the second is a priority, like a latency versus throughput. So in objective, I think in research, there is this very usually you choose research based like a very clear objective. I'm not sure if it's true. You guys please correct me. But I remember when I was doing research, my advisor was like, "Yeah, you should choose a research project with very clear objective so that you can like follow it through and like it's manageable." And in most of the time is probably to aim for like performance, like the model performance, like you probably choose a data set and some benchmark, a little boards that you can like do better than that. So whereas in productions, it's not easily one single objective. Like there can be many different stakeholders, and each of them have a different objective. So for example, for you might have machine learning team, and the objective of this team is to get like highest accuracy, like highest model performance. I also like have a lot of like puppies photos on my computers. I try to insert into talks to make me more likable. So and the next is so machine learning team, you have like highest accuracy as a model perform, like as an objective. You have a product team who probably wants to have like a model with a fast inference because like latency latency costs a lot of money. And then the teams, maybe the sales team probably want to build a system so that they can help them sell more ads. And the next is the manager whose objective might just be to maximize profit, and the quickest way to do so might just be to get rid of the ML team. And it might sound cynical, but you have seen the industry, if you've seen recent layoff like Uber and Airbnb, like the first team to go is the AI research team. So in production, you have different people with different objectives, and you need to find a balance between among them, and to build a system that meets all of the different objectives. So it's a lot trickier. So the next thing is a computational priority. So I think this is one of the more parts that has more disagreements. I will show it to people, and people say, "Oh, that's not true. Like in research, you care about neither fast training, fast high throughput. You just want it to work." So I think that from what I have noticed, I've seen is that like in research, when you train a model, you need to train a model a lot of times, and then you run it like you run inference on the test set, hopefully only once. Like I know some people like run it on multiple times the test set and report the best score. I don't think it's like okay, but people do that, it's okay. But my point is that people do training a lot more than they do inference. So they focus like how to like train faster and make the most out of the hardware. To like if you have those GPUs, something like if you run it on AWS, you probably want to, if you run for an hour, for a day, you want to like make the most out of that day. So you want high throughput. Whereas in productions, you train it once, and not train it once, you have the model, and then you serve it multiple times. So you run inference a lot of times. So you want fast inference instead of fast training. So I think for this time, you guys pretty familiar with latency, and I mean I'm sure people on the lab are familiar, but I'm just gonna refresh in case someone is watching on YouTube, the concept of latency and throughput. So I find the image of an ant carrying a leaf is a pretty good a metaphor for latency and throughput. So if you consider like if the ant can carry only one leaf at a time, then the latency is the time it takes to carry that leaf from the tree to the how do you call like a colony, ant colony. So the throughput is how many leaves it can carry within a certain time frame, for example, like an hour. So it's interesting here because like if the ant carrying only one leaf at a time, so which in term of like in computer term is like you serve a request real time, like one at a time, right? Then it means that if you carry the leaf faster, then you can carry more leaf. So which means that low latency also equivalent to high throughput. But it's a bit more complicated when you serve more than one customers. So imagine the ant carry now not one leaf, but like 10 leaves at a time. So because 10 leaves now are heavier, so it takes longer for the ant to carry the leaf. So which means that it's higher latency. So instead of carry, it take like 10 seconds to carry the leaf. Now it take like a minute to carry 10 leaves. But because it can carry more leaves over an hour, so actually like high latency also equivalent to like high throughput. I'm not sure if it makes sense. Okay. Okay. So yeah. So that's why in productions, like when in training in research, people really like to batch things together. Like, so you have seen a lot of research from NVIDIA, from Google, like people try to flex, like who can like train a model using like larger batch. And then people will say like, oh, this is a batch of like hundreds and thousands of like of a training sample at the same time. Whereas in productions, I have noticed that people are doing more and more like real time, because like the thing that if you try to batch requests in productions, then when one request arrive, and it's like I'm using the term like request. It's just like a proxy term, like like people can use like most of them that use like not like request service, but more like streaming. It's still the same, similar. So like if you wait for other requests to arrive, to process them, to batch them together, then you make people wait more. And I think has been a lot of research done on like just like a very small, more small increase in latency can reduce the conversion rate by like a huge amount. I think it got bought by Google and Booking.com. So like for example, if conversion rate reduced by like 5%, it can reduce like a lot of loss in revenue. So people, so I see a lot of people really trying to do inference like just in real time. Okay, so I think there's the next few parts, like it's a bit more, I can go over quickly for the data. Like in research, you have a static data set. So usually like a standardized data set everyone can use, and it doesn't change as quickly. I have talked to some people at as you Stanford lab recently, and people have been talking about like how to propose like ongoing, constantly evolving data set for research, but it's I think still pretty much work in progress. Whereas in productions, the data changes over time, like and can change very quickly. So for example, it's like if you launch a new marketing campaign, and suddenly now you have like users from a demographics you have never seen before, since the data needs to be updated to reflect the changes. Two other parts are fairness and interpretability. And I think both of them, this point are like also be actually to actively pursued in research, but they're still like niche. Like you can see, like it's not a mainstream part of the evaluation of model. It's more like, oh, if these people care interpretability, then you go to this like interpretability workshop or this fairness workshop. It's not something. It's like it's not a part of the model. Like it's something the main like it's not something. It's not a characteristic of the built-in feature of the model. Okay, so the next part is some of the machine learning production myths that I think it could be pretty common. So the first myth is that people say like deploying is hard. So I think there's some people like scare students like, oh my God, you only have ever take is like Andrew Ng's machine learning course and you can never deploy a model or something. So deploying model actually like pretty easy. So there have been like so many frameworks that allow you to do that. Like you can create very simple. So it has a model, train, predict. You just create endpoints, and then you put them on like AWS and you can access it, and you can use something like Streamlit to just build a simple app, and then that works. I think I've seen demo people doing it in like half an hour. I talked to my friends about it. I think I tried, and it took like about 2 hours for the first time, but like it can be pretty straightforward. But I think there's a hard part about deploying it, how to deploy it reliably. So keeping it just putting it out there is easy, but then how to keep up all the time? How do you do it so that like minimize latency, and then how do you do it so that like if something happened, you can like you can be alerted immediately and then fix it very quickly. So imagine how hard it is to like debug a system in research. They have a model on the computer, just you using it, like it's already like we're already complaining about how hard it is to debug a machine learning model like on the computer. Imagine in productions where like thousands were using it and something goes wrong, like how are you gonna debug it? So it can be very tricky. So a lot of deploying is not about bringing model to end user, but about like to build the entire infrastructure around it so that you can monitor it and you can maintain it, and the right person can be alerted when something goes wrong, and how you can like roll back update if it's necessary. So the next myth is that like you only deploy 1 or 2 ML models at a time. So so it's yeah, so I think it probably comes from also like academic notions of like when you do a machine learning project, you choose a model and it's try to keep on improving it. But I think like when you have a service or when you have an app to users, you have an app might have many different components, and each of them will require different like machine learning models. So I think I saw this very interesting talk by I think it's by Booking or Uber. I think I watch a lot of talks from different companies, so I get confused. But so the key part is that like you have each features, and each feature may require different models, and then you have like if you like Uber, you serve in like 10 different countries, and you might want 10 different models for each model, different model for different demographics. So you have like 10 models, and in 10 countries, already 100 models already. So here, for example, like here's a talk by Netflix. I see like some of the problems that the emotional need to solve. For example, like content valuations, optimize production schedule, like screen analysis. So they own different tasks. So I think so for Booking.com, I think like a few years ago they said they have 150 plus models in productions. Uber is actually a really great company. Like I think I have so much respect for the Uber ML team, AI team. I think you guys have been like being able to build like incredible infrastructure for it. So yeah, like Uber has about like thousands of models productions. So the next point is that it's pretty common. Like people think it's like if you are done, you train the model, you put it out there, and if you don't do anything about it, the performance remains the same. So I think so software in general suffer from something called like we call it bit rot. I'm not sure, maybe we have different term for it. It's like software just generally decays over time. Like if you don't do anything about it, the quality of software just like goes low. Like I would find it very funny when I watch science fiction movies. Like people find like some piece of like alien technologies like 1,000 of years ago, and they go in, they press a button, everything just restart. Like if I leave my code for like a year and I come back to it, like nothing's gonna ever work. Like I don't know, it's just like everything changed, the API changes, and nothing's supported anymore. So software by itself like changes, like it needs constant maintenance. In machine learning is especially more susceptible to this because of something called concept drift. So it's so even a machine learning model is it should build it should find the function to predict like p of y given x, right? With some theta. So like anything can change. For some distributions of your input can change. Your class might change. For example, like if you start a model, Stanford MLSys model by just trying to predict of like whether a tweet is like positive or negative, but then like our team have a different requirement. Now they want like, okay, now we want to be able to classify whether someone is angry or whether it's like very distressed, because for that you might want to like attend to them more quickly than just like normal positive negative. So like that's a task requirement change, or especially come on in medical as well, because like every time there's some changes in the for some new disease or new conditions, and you need to update that a lot as well. So yes, that's concept drift. So I think one tip I have seen that is really useful is to train the model. So like you don't train the model that like have every day all the data you have from the past and randomly sample them, but like more like get the data from like 6 months ago and then train that on the data on 6 months ago, and like do inference, evaluate on the data today. So you can have an idea of like how the model performance changed after 6 months. So you can do that for 6 months, like 2 months or 1 month, just to get a sense of how much the model degrades. And you might be surprised by what you find out. So myth fourth is like you won't need to update the models as much. So that's another part that I get a lot of like contention as well. So people was like, yeah, how fast can update the model? Like people like when you think about the update the model, especially when project managers, they try to like have a budget for it, and they were like, okay, most people think about like when they plan out their project, right? They have a budget for it, but then they think that from machine learning is just like be done with it, and they just put it out there and just own the budget covers. But then they never think about like how often you need to like update it. I think there's just some number I saw about like the 80-20 rule for machine learning is like 20% 20% investment in the developing of models and 80% in like iterative development improvement after that. So I think that people keep asking like when how often you should update the models, right? And was like, should I do it like half a year or like one a year? I think that's a wrong question to ask. The question to ask is like how often you should update the model, like how often you can update the model, not like how you should, but like how often you can. So I think this is one thing that I think we can learn a lot from the DevOps world. So these numbers are the numbers that take from 2015. So so one deploy means just like just one change made into the productions. So it doesn't have to be like for one feature, just like general changes. So you can say that SC only deploy 50 times a day. Netflix like thousands of times a day. And AWS they do like every 11 seconds. So it's not about so I'm not saying that you have to retrain the model every that, but I think that like some gold standards that we should all aspire to, because like every moment that a model is not being updated is some degrade in performance that will hurt the bottom line. So I think I have been like learning more about all about DevOps, and so many concepts in DevOps is just like really mind blowing and they're so useful. And I'm just like, I have this belief that like if machine learning engineers know better DevOps, then the world will be a much better place. Maybe not a better place. Maybe we have AGI or something. But okay. So the next myth is that so people are saying like when we talk about machine learning system at a scale, like latency, like how you serve at the same time, like he says like most people don't have to worry about that. Like how many so they say like, oh, there's only one Uber in the world, there's only one Google, there's one Facebook, there's one Netflix, right? We'll say like, so like most companies like are still like so very small model, like they probably don't even have GPUs ever. And I agree that why most companies are like small and don't have to worry about scale yet. Most engineers actually work for bigger companies. So I think it's a pretty interesting a survey on Stack Overflow. So you can see that more than 50% of engineers work for companies at least 100 employees or more, of at least 100 employees. So it was statistically speaking, most of our engineers are gonna work at a company that has to worry about scale. So that like most engineers should think about a scale. Another myth is ML can magically transform the business overnight. So I think we have been talking about AI. It's like almost like a snake oil, and it can just like solve all their problems. And it's very funny because I think like even recently last week, like a few weeks ago, Wire has this article. It's like very doomsday kind of style. It was like only 11% of companies who have invested have seen a return on investment on the investment. And it was like that number doesn't mean anything because it doesn't take into account of the maturity of the development. Like the companies who haven't seen return might very well have been in very early phase. Like you just started like looking at ML like maybe like a week ago, then there's no way it's not see return yet. So anyway, so I think that's like magically possible, and but overnight, no. Like I think we've seen a lot of companies that seen really great returns on AI. Like I think like I mean, of course, like all the way examples of like companies, for example, like Google, they have had so many models and Google has seen an incredible change. I think for their report recently on like the search on 2020, they said of like they are now like almost all of their English queries are now used and are processed by BERT, whereas the number last year was only 10%, and now it's like almost 100%. I think it's like incredible progress, but also like Google has also been investing in AI for like many years, like ahead of like almost everyone else. So I think there's another graph that I think is interesting. Is a research done by Algorithmia. So how long it takes for companies to deploy a model really depends on how long they have deployed model. So like the more mature the pipeline is. So the more mature the pipeline, the less time it takes for you to bring a model to production. What that means that the less time it takes, like the less engineering cost, and the better the model is gonna be. Because if the model takes like 6 months into production, by that time it's no longer useful. So I think for companies, so I think the company shouldn't expect to see return on investment right away, like a year. I think like companies should be like should manage expectations, and also believe that as more people care about machine learning engineering and MLOps, we will have better tools and better practices. So which means that will help like company should reach some level of maturity faster. Okay, so the next phase is the iterative process that I've been I think like a lot of people have been thinking about. So this is what I call like a 10 out of 10 graph, like 9 out of 10 for content, like 1 out of 10 for style. So the reason I haven't made it like prettier, because it's just like I notice this graph is like evolved over time, and I don't want to like ask the designer to do it before like committing to the final versions. So I think so it kind of break down the different stage in the pipeline. So from project scoping to data management to ML development, deployment, monitoring and maintenance, and business analysis. So the inner layer is a different stages, and the outer, like the middle layers, is what it usually called. So you can see like there are a lot of like confusions around like what is data ops, what is ML ops, what is ML engineering, what is data science, and the outermost is I think the pie chart, like it's like the main skills required at each stage. And here there's only one arrow from a stage to another, but I think in reality it's a lot more complicated than that. So I think that you guys I think for so I think that you guys pretty way familiar with all of this, but I'm just gonna like go over a few points. So first of all, like people like tend to ask like what is the difference between data science and machine learning engineering? And I have talking to companies, and they either have different teams or they like just like don't or they have everything's going data science, or somebody is like, I think Lyft is the companies that have made a lot of change in title. Like this changed everyone from like wait, I need to confirm that. I think Lyft has a huge title makeover that should make the job openings more appealing to people. So I think they made everyone like machine engineer instead of data scientist or something. Okay, I need to confirm that. But what I'm saying is that like my part is just like the roles can be very fluid. So I think like I have several hypotheses on why data science, there's so much confusion between data science and machine learning. So I think to start, for data science data science is when you use like when you use statistics to be able to like look at the data and generate business insights. So data science has been around for a long time, and when people start looking into machine learning, so because they are both using a lot of data, companies think that like so before we invest a lot of money into have our like standalone machine learning team, let's just use our existing in-house, and like what team is the best candidate for that is like probably data science team. So that's how like a lot of people in data science transitions into like modeling. It's just because of the in-company requirements. And also another thing is just like also machine learning can also be used as tools to share insights from data. So for example, like So both of the teams can have like can use machine learning models. So I think Piero, I think you could be like the best person to correct me here. I'm like, are you there, Piero?
I am.
Yeah. So I think it's a very interesting look into Uber. So like Uber has both data science and machine learning team, right? But then like I think for Uber structure is that like data science team to generate insight to have business, whereas the machine learning team to build machine learning products. So both of the teams share a lot of infrastructures in the first one, data management layers. But then you guys like both the teams use machine learning, but they have very different output. So first of all, like price optimizations is it uses machine learning, but is goal to guide business strategy. So that is in data science team. But then for other for other machine learning functions, then it's in machine learning team. I'm not sure if that my understanding is correct.
Yeah, I mean it's fluid, obviously, but I can tell you, like from my experience when I was working there, most of the data scientists were working in product teams and being tied to delivering something specific for the specific product. But then there was also something that was in common, like infrastructure, and machine learning engineers were mostly working on the common infrastructure.
Yeah. So it's like interesting. But some other companies also have different structure. So first one, Netflix. So I know from what I say, like Piero, like machine learning teams more on infrastructure and data science more on business analysis. But then I look at Netflix and they have like different teams. They have a own infra teams that take care of like on infrastructure for both data science and machine learning, and then they have different algorithm team to they work on like machine learning layers. So I think it's a process that like companies are still like trying to figure out, and I don't think there's any standardizations. And so recently talked to a very big company in Europe, and they structure their team like not even based on infra or on skill, but like based on like the stage. So they have a team that's focused on like project scoping, ideations, and they have a team that's focusing on development of model and have another team on deployment of model. So I think that's the space that like people are still very much like confused about. So that's why I'm just wondering. This is a very roundabout way for me to explain that there are a lot more arrows in this than just like one straightforward. But to start, I think like the ML engineering team and the data science teams can share a lot in common. The data management and the deployment teams like have a lot in common because both teams require a lot of understanding of systems, databases, and some machine learning. And in a lot of companies that might be infra layer, ML engineering is what most companies most people are like familiar in machine learning space familiar with, because that's where you deal with like feature engineering, data labeling, developing like models. I would consider like even like model compressions. Even model compressions is more on productions, because like the goal of it is to compress a model enough so that it can put on like production hardware, whether edge devices or like just some like servers, but like to cost less money to do inference. But because it requires a lot of machine learning knowledge, I could still put it in the part of machine learning engineering. And in research, I think you guys are like most people would be familiar with ML engineering part, and not the other part. Whereas in productions, you would have to look at them as a whole. I think did I run out of time? And here's just a step and we talk about it. So yeah, you start with project scoping, planning the budget, managing expectations, and then you go into data management. It's when you think about like how to collect data, how do you track the data lineage, like where's the data, where's the data come from, so like where's store data, how to ingest data. And I think these parts that your lab at Hazy Research like would have so much to talk about. And I think like I feel awkward talking about it with Bate here, because I think that he's like a god of all of that. So yeah, it's a part where you would think about where to store data, how to process on the data, like whether it's like one data lake or data warehouse, or whether you want to deal with like like a query engines, or just something Elasticsearch, or like a combination of everything. And after that, you have the data. You want to like create data set, create training data set, like including the labeling, partitioning, sampling, slicing, and the labeling the data, and then selecting model, training model. And if you're unlucky, you can have to deal with distributed training, which is like still a pain, especially when you want to do with Python. But also like Uber and like OpenAI have been like doing a really great job with that. And they have to evaluate the model and optimize the model or compress the model. For deployment, it's like deploying and serving. So deploying and serving is like deploying deploying is like how to like put your applications on some hardware, and serving is like how to respond to like user requests or user queries. And I think in machine learning, because most of people just do things from like some servers or like in serverless environment, things have been a lot like deploying and serving have been used like, interchangeably. You need to detect and handle data drift. You have to deal with like releasing strategies. You have to like validate deployment. So like monitoring and maintenance is a part that I feel like is still like very much underdeveloped for machine learning, but the DevOps world has like so many great tools. And I think that like a lot of problem with machine learning engineering can be solved by using existing tools from DevOps. The next this data science part is when integrating ML into business. So it has to deal with like business analysis, user experience. I would consider like governance as like who has access to what data, also part of this, but I think some people might consider it part of the data management. So talk about team structure, best practice. I think this tweet is just about like how machine learning engineering is mostly just machine learning and mostly is engineering and not much machine learning. So did I run out of time? Or should I just go talking?
You can keep talking. Yeah, like we're a few minutes over, but that's totally fine.
Okay, yeah. So I think so 4 phases of machine learning adoptions. So the first phase is just before machine learning. I think I realized this quote by Martin Zikovic. So he published this called I think machine learning engineering. Machining. If you like, I think 50 rules for machine learning engineering. If you guys haven't seen this, you should totally check it out. It's like really, really good. So I think he's saying that if you think that machine learning wouldn't give you a 100% boost, then a heuristic can get you like 50% of the way there. So you don't need to like start a product by like complex algorithms. Usually some simple heuristic can work. I think it's one of my first examples to show. It's like the Facebook newsfeed in 2009. So I'm just curious if you guys noticed anything about the newsfeed when it was first launched.
It's chronological.
Yes, that's it. So people think about the newsfeed nowadays, like it requires so much algorithm to like what is the most relevant news like post to show first. But in the beginning, all they did was just like show it chronically, and it worked. And it took them like several more years for them to launch the fancy complex algorithms. So the phase 2 is like when you decide like, to go with machine learning. I think it's always good to start with something really simple. And I think like something simple like so it has several purposes. So first is like to validate the hypothesis. Like you have the data and the hypothesis that this data gonna help you do something useful, but then you can't really. So if like simple models doesn't have you do anything, doesn't necessarily means that it's not gonna. It doesn't necessarily mean that it will never work. So anyway, I think I'm just like going round about here and say like having a simple models will allowing more visibility into relationship between the data and the output. So you understand like, so you can see whether the hypothesis makes sense, and also having validate the pipeline. So I think Google has a talk about like earlier this year about when they like analyze the post-mortem of like 96 machine outages in the system, and they found out that most of the outages are not caused by machine learning, but by just normal engineering, because something with the pipeline, especially the distributed pipeline. So when you have a simple model, it allows you to debug it, and only when you have a pipeline you can trust that you move onto the next phase. So the phase 3 is when you so you have the pipeline. You think that like so hypothesis makes sense. Like there's definitely some patterns you can learn from the data. Then you can try to like optimize the simple models. So you can do something like you have different objective functions. You can do feature engineering. You can collect more data. You can do ensembling. And I think like simple models still like have a lot of power. It's really powerful. I talked to a lot of companies and still tell me that it's very hard to just beat something like XGBoost or Dysentery. So anything like I think for Kaggle conventional students that has changed, but like just until a couple of years ago, most winning solutions are not deep learning, but still like simpler models. So phase 4, after you have done everything, and I think it's going great. So I think now it's time for you to like try out more complex machine learning models. So here's some of the principles of good machine learning system design that I think like it would, of course, it's gonna take more work on like explaining it. But I think like for first is like it has to solve a problem, and I think like it seems obvious, but you will see like a lot of companies they use machine learning like either because they don't want to miss out, it's like very much FOMO or like driven, or they just think that if they say they use machine learning, then they get more customers because it sounds more like edgy, like cutting edge. But the problem with like with a system, if a system doesn't solve an actual problem, then it itself might be a problem because it will cost you more maintenance and it just costs more. Like it has to be tested. I think this is a lot more of that. I think the time is running out, so if you guys wanna like discuss this, I would be happy to. And also like teaching the next course next quarter is on exactly the same topic. So I think it's open to SCPD student as well. So let me know. Thank you guys.
Thanks so much. A really great talk. Yeah, we can definitely dig in a little bit into some of the points in your principles of good design. We had a bunch of questions coming in, so let me start by kind of asking a couple of those. So we got a couple of questions around some of the myths that you talked about. I think Pat Langley had a few questions around those. Like one of the questions he had was around deployment. So I think one of the things he pointed out was maybe deployment can vary across applications. Like let's say medicine, it might be slightly harder to deploy non-image based models, for example. So he was wondering if you had any thoughts on whether deployment is always easy or hard, or if there's some guidance on like settings where it is typically harder than the examples that you gave.
So I think like the question of whether deployment is hard really depends on what applications, like certain case by case. So I think like there are several bottlenecks that I think they can see in the term of medicines. So I think like for medicine, I think there are several challenges. Like the first is practical challenge, as in so I think this is just based on a talk one of my coworkers like Brandon Yang just gave recently, actually. So I'm just like copy and paste his talk here. So the practical challenge is so first of all, it's the data annotations, like getting data. It's very hard getting patients' data, right? And then if you label the data, it's first like to label medical data, you need like domain expertise. So you can't just ship it out to someone on the Amazon Mechanical Turks, and because they are not trained. So it's very costly to like label every sample. And second, it's slow. And third, that like it requires privacy. So you don't just want to send data to like even with expertise, but they're not part of the system or something. So you very likely need somebody to like sit on site or like go through a lot of like training. So it's very hard to acquire data for medical. And second is yeah, and the format of the data. Some medical data is it's very tricky. So you mentioned something non-image data. I actually have seen that in productions. Textual data actually like is easier to deal with than like image data. And also like, but in medicines, it comes like in many different formats. So you have text data for some medical record, doctor notes. they have like image data and image. Then the medical image is not just like a pixelated like cute something like they can be the CT scans, and like each of those like very large, and you some like because some of them like might not even fit into the memory because you're just like really large. So it's hard to deal with. And also like if you work with like for drug discovery or something, a lot of data can come in like in a graph format, like knowledge base. And also like it's very hard to figure out like the time frame. So like for if you track a patient, you would say that like you would say like, oh, that person, like if it's ideal, that person come in for check-in like every 6 months, right? But people don't do that. Like so if you want to treat them as time series, it's a lot harder because you don't know how to like quantize a different time, like how much would like 2 years lapse different from like 2 weeks lapse. So it's there's a lot of it. And another, so that's like a bunch of practical challenges for medicines. And another is the ethical challenges. I think medicines is one of the field when like interpretability of fairness, like extremely important. I say like one of these like important like in other applications, but it's just like more so when you directly deal with like people's life. So like to have like people to trust and use AI system is still a long way. Do you guys remember Jeffrey Hinton tweet about like a year ago when he was asking like if you have like one is like AI surgeons that have like 90% cure rate but can't explain like why, and have like a doctor with an 80% cure rate but can explain like which one should be made illegal. so I think that's a question of even like AI like has provably higher cure rate, like people might not still want to use AI just because they can't explain.
I actually have a follow-up on the point of that Karan raised about the myths, because also from the chat, there's many people interested about some of those myths, and I have one specific experience with some subset of those that I'm really curious to hear your thoughts about. In particular, I think one that is particularly interesting is the notion of shift and distributional shift and concept drift, and anything that basically changes the what kind of data you observe when you deploy the model with respect to what kind of data you train it on. And I think it also connects with the retraining strategies and updating the models. Do you have suggestions about this, how to deal with this kind of phenomena?
Yeah. So I think that's a great question. I think like you just like touched Ryan, that like huge bottlenecks that like nobody knows what to do with in ML. So I think I try to like give like somewhat like a brief answer of what I think like think about it. So I think the first thing is definitely you would need to monitor it. So I think it's pretty funny because I used to ask this question to candidates, and they were like, yeah, just monitor it based on accuracy and how accuracy changes. And I was like, wait a second, in production you don't have like label data, so you can't really like monitor the accuracy. If you're lucky, you have like real-time feedback. For example, if you have a recommendation system and can see immediately if people like click on it or not. So if you have a system that's like somehow tied directly to our end business goals, then you can notice the difference first of all, like when there's some major change. For example, if conversion rate like goes down, or if like click-through rate goes down. But it's also very tricky because so Google recently made a huge change in the systems. Not recently, I think about like 2 years ago. So you guys noticed that like Google went from a search engine to a question answering engine. So like before, like you enter a query, right? It show you like on the search results. But now, like it's since the recent change, it's like you answer a query, like if had like some highlight question, like answering on top. So like they try to show you the answer immediately. So I think like at that time, like when Google made that change about a few years ago, like a lot of people who work in like advertisements like freaked out because sadly the click-through rate, like not click-through rate, like the I'm not sure what even they call it, like they're just shown rate. So before like you care about like if users like search for something, you want the result to show like in the first page, right? So with the change, suddenly like owners are changing, like a lot of them like saw very much lower like first page result. But it didn't have, so at first people thought it was like a bad thing. but then they did more digging into it, and they realized actually like increase their revenue, because Google became so much more efficient with how they show the results, that even though it appears less, like people who sees actually only when it shows that it's actually really relevant to the search. So actually like they have higher people like finding what they're looking for. So what I'm so like, it's a roundabout answer, but my saying is that like it's a lot trickier to figure out the direct relationship between the changes, because a lot of the time because we don't have like the actual accuracy, like we have to use a lot of proxies, and proxies can be misleading. So one example is just like okay, I think you can go more and more into that, but I think let's like focus on the question at hand. So yes, first of all, you have to monitor, and if you can link it to like direct users feedback is great, or direct business goal is great. And the second, it's like you have to define different metrics. So because we can't use so like if so you can use a lot of different metrics for both data. Data and models. So I think like Google or like GitHub recently, GitHub Actions actually, I think did they buy great expectations? So basically you have a you define like the range for different input data, and it tries to see whether when any of them goes out of the expected range. So for example, like if you think it's like, oh, this feels easily like people feel it about like 90% of the time, but now it's like half of them are none, like people just don't enter anymore. So something has changed. So it's just like more fine grained of what you want to monitor. You also want maybe more monitor like how the models output. So you just like a lot of them, it can be defined. For example, you think it's like usually the models like could predict this class like 90% of the time, and there's a class like 5, the class at 2%. You can see when that changes over time. And I think like for this kind of things, like we don't really need specific machine learning tools. I feel like for tools and New Relic, the only you have is just like you emit, you define metrics, and it helps you like monitor those metrics over time. And you might need a different things to like analyze the metrics and see whether something has changed. I'm not sure if it makes any sense.
No, it did, absolutely.
Yeah. So yeah, so monitoring is big. And I think yeah, so and a big part is really interesting. Is I think I have seen is like tracing. So for example, like if you have a system so like with a lot of different components, so like when users input something, right, it might go through multi different things, and until it like output, and you have no idea when is that it's gonna at which part like something breaks. So you have to give them like some ID, so they can like able to track that through like different steps, and be able to like just like have you like debug when what goes wrong. I think it's really useful, like especially useful for during the development of the machine learning models as well. It's like the ability to just let you like step through the systems and just see like what is the expected output at each step. And I think that a lot of people don't pay attention to it, because in training they will just care about like doing things at batch. But like if during the process layer of the pipeline, if you can just like allow the model to just take in one single input, and during the time, it's gonna be very useful. And also another thing is like really interesting to have seen people do, and I think that everyone should do that, is that if you look into those systems, usually like the feature engineering for training, for development and deployment actually different. It's because like in feature engineering in training, you do them in batch, right? But during development, you do that like each sample at a time. So like in theory, you need both of them to do the exact same things, but like in practice, you have different pipeline. So that's actually caused a lot of problems. So like one thing that you should really do everyone should do is just like making sure that a sample that is not output one the exact same output in productions as is in training. So one thing is just like try to log on the input systems. It can be very useful because you can then use that data as a training data for the next iteration of the model as well. I'm not sure if it makes sense. I have seen a lot of bugs like that. It's just like somehow like you have a model, like you have a train of pipeline, you get the sample, you do it through the training and it's output one thing, and then when you do it like on inference, it's just like output different things. It's sometimes that you do it. Sometimes it's like because of difference in the feature engineering, but sometimes it's just like some like stupid routing error. So
cool. A lot of sage advice for our viewers, I think. You mentioned early on in your talk that one of the differences between ML and research and ML and production is that in research, things like fairness and interpretability are nice to haves, whereas in production, they're much more important. How do we get ML researchers to pay attention to some of those other things, metrics that aren't just top one accuracy, and prioritize some of those other metrics more?
That's a great question. I think that's one question I think the research community is like actively being like working on. I think I realized the idea of like adaptive utility leaderboard. So I think we need to understand like what researchers are motivated by, right? And I think you guys probably know this way more than I do. But I think I found my very brief stint trying to do research. I was considering doing PhD, and then some of my professors were saying just like, you don't have any top tier conference papers, you need to like work on it more. And so I went to work for a year, and then I never came back because working is just fun. So like during the research, I feel like people care a lot about leaderboard, like soda, reviewing paper, like everyone put like, oh, we beat soda by this, by that. And if you get some like super glue leaderboards, it's super exciting. Or like, do you guys like obsessed with like papers with code and see like what models are performing best on different data sets?
Usually when you're working on the paper and trying to get soda, that's when I check the most.
One of the problems there, is the fact that if you just look there, you don't know how many resources were put into training those different models, how many upper parameters were tested. And so comparing directly by looking at the numbers that are coming from the papers, it doesn't seem, I mean, it's an indication, but doesn't seem to be the solution to the problem, really, right? Yeah.
So I think it's because research has like different objective, whereas like production have different objective. So, and I think like the values of models is very different for different users as well. So like for one users, they might care more about performance. For another users, they might care more about interpretability, and another users might care more about like some like inference costs, for example. So I think like instead of having one single leaderboard for one data set for one task, we should have an adaptive leaderboard. First of all, you can specify like, oh, this is like extremely important to me. This is like somewhat important. This is like not important. Then you have a leaderboard that show that. So but the question is like, how do we like measure that? And I think this, I like this paper by Huyen and Dan Jurafsky. It's a paper from Stanford. It's about like a critics of NLP leaderboard. And I think they propose something like utility functions. So I think they have different, so they define different variables for the utility, and then it calculate utility score for like depending on how different importance of variable is for you. I think Don Bench, I think it's just the work from Hazy Lab, right? Or Hazy Research, or is it different lab? Don Bench.
I was very involved in Don Bench.
Yeah. So I think Don.
Yeah, go ahead. Yeah.
Yeah, so I think Don Bench is very interesting. I think you guys want to try to benchmark on the time it takes to the inference, right? So I think it's a great initiative. Yeah, I wish like more people do that. So I think it was looking at Don Bench, and the last thing you have was like from 2000, like quite a few months ago. Do you find like what difficulties do you have in like for people to like run the models on the bench?
Well, so the on-bench has mostly been superseded by the MLPerf benchmark, which has even more organizations involved. So like all the students who are working on it have, are contributing stuff to MLPerf, and that's running pretty regularly. And it's comparing a lot of dimensions of hardware efficiency, both for training and for inference. You can also use it to compare dollar costs on cloud providers and stuff like that.
I think that's great. So I think so like so that's just one of like different type of, I don't think it's leaderboard. I think it's a different kind of benchmark, like metric for people that you care about, like inference or like hardware usage. I think MLPerf is very interesting because every year I look at MLPerf results, like different companies and represent the result differently. Like Google will have different graph from NVIDIA, like NVIDIA graph somehow show NVIDIA on top, and Google graph somehow shows like Google on top. So like it's just like people like still have different way to interpret different like the metrics. I think I heard also like the team at Facebook, I think it's Dino Bench or like something like that. I forgot the name. So trying to like, so the idea is just like if you have a model, you just like ship them the weight, and then you can like output some kind of like different criteria, like it's gonna measure the models on different metrics. So I think that's working actively in progress. I think that eventually maybe we can even have like a machine learning model to like predict what the different iterative for models for a task.
Chip, I wanted to ask a question about your diagram for the ML kind of production lifecycle. I noticed that ML engineers didn't seem to require any knowledge of the system that their kind of output would be put into. And I thought that was maybe a little bit controversial. Maybe you can elaborate on why you think that is. To me, it sounds a little bit like, a civil engineer has to build a bridge, but he has no idea how wide the river is, or like what dimensions of where this thing line should be installed. And I was wondering, is it really that different when you're designing an ML model with regards to how much you have to know about the system at hand?
When you say the system at hand, like what do you mean system?
So basically, the model is going to be placed into a system and served, and data is going to be loaded into it. But what I mean by that is kind of like the physical constraints and the software and hardware constraints that are present.
I think that's a great point. I think there's a point, like actually my friend, have you guys seen the paper, the hardware lottery by Sarah Hooker? I think it's a really great paper. It's a her idea, her hypothesis is like a lot of research is like some research ideas get more popular, not because the ideas are better, but just because they are better suited for the existing hardware. So so in the past, like software and hardware are like very much like hand in hand, but somehow at some point diverge. So like software people do their own thing and hardware people do their own thing. So like software people might come up with algorithms and like they have no idea how these algorithms can run, like how to implement hardware, and the hardware people like develop hardware is like are not really supportive of algorithms. So I think it's very interesting. So this is one hypothesis that I heard a lot. It's about the capstone network, like how capstone is like such a brilliant idea, but then like it never caught on because it's like never been able to find a way to like run it on like GPUs. So it's an example of like a research idea that seems like brilliant, but then it just like doesn't work with existing hardware. So I think the point is absolutely right. It's like people who build and machine engineering should know more about like the underlying aspect of it. And like I think like a lot of people are doing that, like trying to like build think about the system like as a system as a whole, both hardware and software, and not just like software will do their own thing and hardware will do their own thing, as in by luck some of them are like work together and then build something meaningful. I think like Apple is a company that's like doing pretty well. Like they trying to like do both. Like they have their chips, like they build their own chips for machine learning, and then they build applications for it. But I think it's sad that Apple is like way too secretive. So like a lot of the claims they make, like it's hard to verify. and also like it's hard like for the community. I think NVIDIA is doing great on that as well. Like they also have but like inside NVIDIA, yeah, it just seems yeah, I think NVIDIA is doing good. Google is so excellent at it. So I'm not sure if that answers the question. I know I was going to a rant.
Yeah, it does. Thanks.
Right. I think we're only a few minutes over, so I think we got a lot of the questions in, but I'm gonna sort of close it out now because I know a lot of people probably want to move out after 4 o'clock. So I want to thank you, Chip. I think there's one question I want to ask you that people are actually curious about. Will the course videos be available online and publicly?
Oh, why do you have to ask that question? So I'm thinking about it. I mean, I would definitely discuss with some people, because the course is not gonna be like my course, and like it's gonna be a work of like multiple people, including you, Karen. So so I think it's definitely like anything that I want like to put online, it's gonna be a discussion of the whole team and not just me. And also like with Stanford as well. And I think I try to, I'm a huge believer in open source. So I think like if I can, just anything that I can put out, I will. I will try to, yeah.
And I'll definitely help with that. So hopefully in the chat, we'll try to get something out to you guys so you can take a look at the course material. So I really want to thank you, Chip, for spending time with us and taking out time to share your thoughts on machine learning and systems. And I want to thank all our audience members. If you're not subscribed to our mailing list, go to our website, mlsys.stanford.edu, and subscribe. If you are subscribed to our mailing list, we actually send out a small 30-second survey for soliciting some sort of feedback on topics that you'd like to see when we're back in January. If you're still around, of course, next week we're going to have Roy Frostig talking about JAX. And last thing, do subscribe to our YouTube channel. It feels weird to say this. I see all the YouTubers that I watch say this, but yeah, do subscribe and keep in touch. All right, thank you so much. I'll wave to our audience. Bye.
Thanks for having me. Bye-bye.